All right, hello. Today I have a presentation for you that is called Limiting Reagent and Amount Produced. Now what I'm going to do is just have a very general discussion very quickly. You already know what a balanced chemical equation is. You know that in fact, you know that a chemical equation represents some type of reaction. So in other words, maybe we would have x plus z equals xz. Well, what would that be? Well, that would be a synthesis or a combination reaction. Now, there are more than one. There's more than one type of chemical reaction. So when we look at the particular reaction and then we go for the lowest whole number ratio, okay, well, what are we doing? We're looking at the lowest amounts that have to react in order to make that reaction occur and to get a certain product, okay? But, understand, those are the lowest whole number ratios. Well, what happens in real life when you have differing quantities? In other words, what if you have X amount of reactant, or what if you have more reactant one time than you do another? How does that all work? Because I think you're intuitive enough and smart enough to know that in the real world, you could have a particular reaction occur, but you could very well have differing amounts or differing quantities. All right, so how does that work? Well, let's discuss that today. So let's start with a balanced chemical equation like N2 plus 3H2 is equal to 2NH3. All right, and let's look at that and let's say, okay, in real life, what is this? Well, it's a balanced chemical equation. What is it? It's the lowest whole number ratios that represent this, and once again, you can see that this is a combination reaction. This is one of literally who knows how many, thousands upon thousands of different chemical reactions, I suppose. I don't know what the number is, but this is just one example. But for this reaction to take place, to produce this, you would have to have this and you would have to have this. And this would be the lowest ratios that would make this happen. So if you wanted to make, some NH3, right? Then you would have your N and your H present in a what? Well, it would be present, as you can see, in a 1:3 ratio. All right, don't overcomplicate. You're like, okay, I understand that. This particular reaction, that's what we would need, and that would be the lowest whole number ratios. Yes, but what if you didn't have 1 mole of N2? What if instead I told you you had 2 moles? What if I told you that you had 2 moles, but everything, the amount of hydrogen was still the same, but instead of only having 1 mole, you now have 2? Well, in my mind, that would beg some questions. It would beg the question like, would you make more product then? Just because you all of a sudden have more reactant, do you necessarily make more product? Would everything be used up? How would it work? Okay, there are questions here that I think I would want to assess. Well, here it is. I want you to think about this. I want you to think about the fact that in the first equation, you were present in a 1:3 ratio right here. But then all of a sudden, I tell you, you have more of this. So make no mistake, I'm telling you that instead of only having 1 mole, you now have 2. But what did I not change? Well, I didn't change the amount of hydrogen that you had available to you. So I think this one is pretty simplistic, but I chose a simple one because I thought that you would be able to see the main point. The main point here is I'm still going to make the same amount of product, but I'm going to have some leftover nitrogen. Now, I want you to consider this because I think in principle, it's not all that terribly complicated, if we just make it simplistic. If I told you that I wanted you to build something and I only gave you 50 screws, then at some point, I think you're going to have to think about the way you put it together, because you can't put it together in a way that requires 100 screws because you don't have that many. So, maybe you have more than enough board or you have more than enough whatever, but if I've limited you in one of your quantities or one of your reactants, if one of them is limited, then don't you think that's also going to have a limit, effect on how much product you can make? In this particular case, I told you, hey, let's increase the amount of nitrogen, right? But we left the amount of this reactant the same. So essentially, we end up with the same amount of product, but we have some leftover nitrogen. Okay? Well, so here goes. I want you to think about this. We can think about this in one of two ways. So let's think about hydrogen and then come back to nitrogen, which was the one that we increased. But let's start with our hydrogen. What did we do? Well, we completely used it up. I mean, you have you have 6 atoms right here, and you have 6 atoms right here, so it's obvious we used it up. I have some nitrogen left over, but let's talk about the hydrogen for a minute. I completely used it up. It is the limiting reagent. It is the screw in this example, right? In other words, you can only make a certain amount of product because this is the one that's holding you back. You're limited. Okay, well, what do you mean? Well, this one was left over. You had some left over, so obviously it was in excess. Excess is to mean to have more than what you need. So in this particular case, you increased this, but you didn't really increase your amount of product. You just had some of it left over. Okay? Now, what if you had increased this and increased this? Well, then we might be talking differently, but we didn't. So this, okay, in this particular case, when I increased the amount of nitrogen, this one is the one that limited it. Okay, so it's my limiting reagent. This was left over, so it is my excess reagent. Well, don't you figure that there's probably going to be a lot of times in life where a reaction is going to be inhibited by the limiting reagent? And maybe there are times when we need to identify that reagent. So I'm going to give you a reminder before we get mathematical. The reminder that I'm going to give you is who's your buddy? And you know that your buddy is the mole. Now, why is your buddy the mole? Because as we have discussed many times in this class, this is a very unifying, this is a very central figure. The mole is a very central figure because of my ability to go from something else to the mole, or my ability to go from the mole to something else. And obviously you can see that I have multiple arrows there because not only do I have multiple avenues in, I also have multiple avenues out. So I want you to read this statement with me because it's going to become a foundational statement for the rest of this presentation that we're going to look at several times. It's a mouthful, so we're going to break it down. Here goes. Sometimes in stoichiometric problems, the given quantities of reactants are expressed in units other than moles. In such cases, the first step is to convert the quantity of each reactant to moles. Then the limiting reagent can be identified. The amount of product formed in a reaction can be determined then from the given amount of limiting reagent. Now that's a statement, and you're going to have to slow down and you're going to have to read it and you're going to have to think about it. But right now, think about it in 3 parts. We may have to convert to moles. Once we convert to moles, we can use that information to help us determine the limiting reagent. In other words, which one is holding, the production of more product, which one is holding that back. And then lastly, if we know the amount of limiting reagent, we're going to be able to calculate how much product it is possible for us to get from that reaction. So moles, limiting reagent, and the amount of product. All right, so let's begin with let's put this into work. Let's look at this and analyze it mathematically. So copper reacts with sulfur to form copper 1 sulfide according to the following equation. Now you're going to look at it and you're going to say, okay, Mr. Day, I understand that is a lowest whole number ratio balanced chemical equation. I understand this is a synthesis reaction for those particular reactants to get this particular product, okay? So this reaction is for, this equation is for this reaction, and this reaction only. And so we look at it and we see the lowest whole number ratio. Now here's the real question. The question is, okay, it's good that we know, but in real life, how much do we have? How much of this are you going to give us, and how much of this are you going to give us, and which one is going to be the limiting reagent? Which one's going to be the excess reagent? How's this going to work? Okay, well, here goes. I'm telling you now that we're going to give you 80 grams of copper and we're going to give you 25 grams of sulfur. Okay? So which one of the two is the limiting reagent? Well, what did we say a while ago? So slow down, read it again. Sometimes in stoichiometric problems, the given quantities of reactants are expressed in units other than what? Other than moles. So what do? In such cases, the first step is to convert the quantity of each reactant to moles. Well, so that's not a problem. You gave me grams, so I can easily use molar mass, and I can easily make a conversion factor, so I can easily convert from mass to moles. Sure you can. So what do? You take your 80 grams of copper, you multiply by 1 mole of copper over 63.5 grams of copper. Where'd I get that? Straight off the periodic table, that's molar mass. I do my problem, which means I'm going to end up dividing this by this, and I get 1.26 moles of copper. So that's if I have 80 grams, okay, if I give you 80 grams, this is how many moles of copper that I have in this example. All right, I have 25 grams of sulfur times 1 mole of sulfur over 32.1 grams of sulfur. I'm going to end up dividing. I'm going to get 0.779 moles of sulfur. So if I give you 80 grams of copper, you have 1.26 moles of copper. If I give you 25 grams of sulfur, you have 0.779 moles of sulfur. So what have I done? I've taken the quantity that you've given me, Mr. Day, and I have converted it to moles. That's all you've done so far. Okay? Here we go. Sometimes in stoichiometric problems, the given quantities of reactants are expressed in units other than moles. Ours was in grams. In such cases, the first step in the solution is to convert the quantity of each reactant to moles. So what did we do? We took our grams and we converted to moles. Now what? Then the limiting reagent can be identified. So we took our masses, we converted them to moles. Now we need to identify for that particular reaction, so for this reaction, which one at 80 and 25, which one is our limiting reagent and which one is our excess reagent? Or are they equal? Are they all used up? Let's find out. So we converted to moles, and when we converted to moles, we got 1.26 and we got 0.779. Now what are we going to do? Well, we're going to pick one of them. Which one? It doesn't matter. You can get to Bloomington more than one way. I'm going to take the 1.26 moles. Okay? So stick with me here. So what are we going to do now? We're going to take the 1.26 moles. And here's really what we're saying. We're saying, okay, if that's how many moles of copper I have, and I'm going to carry out this reaction, okay, then given 1.26 moles of copper, given that, how many moles of sulfur would I need? So I'm going to use the molar ratio. The molar ratio, which comes straight from the balanced chemical equation. And I'm going to convert 1.26 moles of copper to moles of sulfur. Now why? Why am I doing that? Okay, because if I know how many moles of copper that I have, and I use the molar ratio, that will tell me how many moles of sulfur that I have to have in order for this reaction to take place according to the lowest whole number ratio balanced chemical equation. So when I do that, okay, so when I do that by using the molar ratio, here's what I come up with. And you can always pause this and take a look at it, but I come up with 0.630 moles of sulfur. Well, but how many was I given? Oh yeah, this is how much I was given. Yeah, this is how much I was given, and this is how much I would need if I had this much, and I'm considering this reaction and using the molar ratio from that reaction. So if I have this much, I need this much. But Mr. Day, you said you gave me this much. That's right. Then what does that tell you? That tells you that you have more than what you need. So obviously sulfur is not going to be your limiting reagent. Sulfur is going to be your what? It's going to be your excess reagent. So then you're guessing, oh, well then I'm guessing that copper is going to be my limiting reagent then. Yes, but if you want to know for sure, do it in the opposite direction. So take this value that you calculated a second ago at 25 and turn this value not into moles of sulfur, but turn it into moles of copper. So in other words, if this is what you had and it was going to be pretty much even Steven, right? Then if you converted this, what would you get? So that's what you do. So do it in reverse. So Mr. Day, okay, I'll take the molar ratio and I'll convert from moles of sulfur to moles of copper. But when I do that, I find out that I need 1.56 moles of copper, but you were only given 1.26. How do I know that? Because we calculated it here. So if you were only given 1.26, but you need 1.56, you don't have enough. That makes you the limiting reagent. So in this particular case, you were able to calculate which one was the excess and which one was the limiting. Go back to your statement. We're almost finished for today. Sometimes in stoichiometric problems, the given quantities of reactants are expressed in units other than moles. Yours was in grams. In such cases, the first step is to convert to what? To moles. So that's what you did. You converted from grams of given, okay, to how many moles you were given. Then you figured out which one was the limiting reagent. Well, when you converted copper into moles of sulfur, you found out that you had more than enough sulfur, but you didn't have enough copper. Well, I wanted to check that to make sure I was right, Mr. Day. Well, then you converted moles of sulfur into moles of copper, and you found out that you didn't have enough. The amount of product formed in a reaction can be determined from the given amount of limiting reagent. So stick with me because this is the last part. Same equation, same molar ratio, same balance, same numbers. I'm going to give you 80 grams of this, and I'm going to give you 25 grams of this. But what I really want to know is I want to know how much of this in grams, how much of this can I produce? And you're like, hell, I already know which one is the limiting reagent. I know that copper is the limiting reagent because I just figured that out a while ago. So I know this is the one that's going to hold things back. Good. Then that's the one you're going to use to determine how many grams of this you have. So how do you do that? Well, I bet you're a step ahead of me. You're going to take moles of copper and you're going to convert that to moles of product. Well, when you do that, you're going to almost be there because you're going to be like, okay, Mr. Day, but I know that's not what you asked for. That's not what was asked for. I wasn't asked for how many moles of product. I was asked for how many grams of product. I bet you know how to get there because where are you at? You're in the mole already. So what are you going to do? Well, you're going to say, okay, once I'm in the mole, I remember this slide you showed us earlier, once I get in here, I can go just about any direction I want. So I can easily come out of mole and go to grams if I use molar mass. Sure you can. So what are you going to do? Last slide. You're going to take moles of product, you're going to multiply it times molar mass, and when you do, you're going to come up with 100 grams of product. Based on what? Based on your limiting reagent. Because it is your limiting reagent that is going to place the limit on how much product you can make. So what do we do? Well, I'll tell you what we did. We took a lowest whole number balanced chemical equation for a particular reaction type. I gave you grams of product. You converted to moles. And then you decided which one was the limiting reagent. And then once you knew which one was the limiting reagent, you knew how to calculate how much product mass you were going to get.